Let's do a two-dimensional example next. Let's use Gauss's law to find the electric field around a plane of charge. We're going to use the idea that our plane of charge has a positive charge density sigma. Remember, this is our area charge density. It's going to be the charge divided by the area, measured in coulombs per meter squared. Our first step in the process is to write Gauss's law that says that the net electric flux through any Gaussian surface is the integral of E dot dA, and that's equal to the net charge divided by epsilon naught, the net charge within the Gaussian surface. If we want to use Gauss's law, we know it applies to a Gaussian surface, so we're going to have to choose our Gaussian surface, and to choose our Gaussian surface, we need to think a little bit about the electric field of a plane. Let's start to think about the electric field around a plane and how do we pick the appropriate Gaussian surface. So our plane just looks something like this. Yes, it is a little piece of Legos. What we know about the electric field of a plane is that if our plane has positive charge, the electric field vector sticks out in both directions. So it points up on the top and it points down on the bottom. That's what the electric field vector looks like. We want to pick a Gaussian surface. What we generally do is pick something that matches the symmetry. The reason why we pick something that matches the symmetry is it makes it easy to do the integral. So something that would match the symmetry of a shape like this would be a box. Let's make our Gaussian surface a box where part of the box sticks off the top of the surface, like this, and part of the box sticks out of the bottom of the surface, like this. Okay, now when we go to do our integral, all of the vectors are either going to be parallel or perpendicular. So our electric field on the top points straight up like this. Then the area vectors on our little cube that points up out of the top, points perpendicular out of each side, and then for the front and the back, points front and back. So all of those vectors, when we do our integral of E dot dA, everything's either going to be perpendicular or parallel. So for us to find the flux is not going to be that difficult. So our choice of Gaussian surface, something symmetric and useful, is going to be a box that sticks out on both sides. So this is supposed to be a 3D version of a plane. So if I draw a box that sticks out on both sides, my drawing skills are going to go downhill really quickly here. So here's my box coming out the front of my plane. And my box will also stick out of the back of the plane. Okay, so there's my 3D drawing. I've got this drawn with the computer on the other side, and I think that computer on the next slide, and I think that computer drawing is probably a fair bit better. So here now are my nicer computer drawings. The pink arrows coming out are the electric field vectors. Let's just label those E. And then the box shows my Gaussian surface. So why don't I just label that Gaussian surface? I have three different views here in my picture. I have a side view, so if you imagine you're looking at it from right here, so that shows my Gaussian surface is this guy, and my electric field vectors are these. And then you could also imagine you're just looking at it from the front, so here's the top bit of my Gaussian surface. And then this part, trying to get my laser pointer, this part is the whole plane itself. In this case, if you're looking at it from the top, the electric field vectors are coming straight out at you. So we're going to use Gauss's law, remember. The net electric flux is the integral of E dot dA, where A is the area of our Gaussian surface, and that's equal to the net charge enclosed by the Gaussian surface divided by epsilon naught. So to find our charge enclosed, we're going to use the same approach we used with our line of charge in that we're going to do density times the physical size of our object. So let's write that down for our Q enclosed. Q enclosed equals density times size. So let's shade in what we mean by the area of our Gaussian surface. So we're asking how much charge is enclosed by this Gaussian surface. How much charge is on this bit of the area here? We can indicate that in all of our pictures if we wish. So here's our Gaussian surface. This is the part that has the charge. So Q enclosed equals what? And of course over here on this part. So it's not going to be the total charge, it's only going to be the fraction of the charge. Our charge density is given, that was sigma. That's the total charge divided by total area. And the size of our Gaussian surface, we'll say, is A. Since we have a plane of charge, that's a two-dimensional object. By physical size, we mean the area. Okay, that deals with our Q enclosed. Next, we have to deal with E dot dA. Let's put our results together now. The integral of E dot dA, the net electric flux, or the number of lines cutting through our Gaussian surface, is equal to the charge enclosed divided by epsilon naught. We know the charge enclosed, and we figured out the net electric flux through the entire Gaussian surface, that whole box. So let's write down our Gauss's law. E dot dA over the whole surface equals Q enclosed over epsilon naught. 2 times E times A is equal to sigma times A. Notice we've got an area on both sides. That's kind of an interesting result. The area of our Gaussian surface, it canceled. That means you didn't really have to pick a box here. You could have picked a cylinder or some different shape because overall it's the area that matters. I picked a box specifically because it matches the symmetry of our plane. A plane looks like a box. A lot of books you read, they might pick a cylinder here. They call it a pillbox for historical reasons, but I like the idea of using a box. All right, let's solve for our electric field. So E is equal to sigma over 2 epsilon naught. Of course, electric field is a vector, so the direction is outward and perpendicular to the plane. Outward because it's a positively charged plane. If it were negative, it would point inwards. So now to start dealing with the left-hand side of the equation, the net electric flux given by E dot dA, we have to ask about the area of our box, which is our Gaussian surface. So our Gaussian surface is the box. How many surfaces does a box have? So our Gaussian surface has a front side. So here's the front, or over here. It has a back. Here's the back. And it also has the sides. So these are the sides right here. So our surface has front, back, and sides. So if we want to get our net electric flux, that equals the flux of the front plus the flux of the back plus the flux of the sides. So you might be feeling like this is similar to what we did for the line of charge, and that's true, it's exactly similar. All these problems are pretty much the same, and if you take the same standard approach, you'll probably get it right every time. Okay, let's do the front first. So what's my net electric flux through the front of my box? First, I'll shade in the front. So that's on my 3D view. On my side view, the front, I suppose, will just show by this line. So the flux through the front is the integral of E dot dA. Let's show what our dA is. It's a little bit of the area vector. And dA sticks straight out this way. If you were doing this on a test, it would be okay if you picked one view or the other, either the side view or the 3D view, whichever drawing you feel shows your work the best. So our dA sticks straight out and our electric field sticks straight out. So we see that our electric field vector and our area vector are parallel. So the integral of E dot dA is the integral of E times dA times cosine of 0, because E is parallel to dA, equals the integral of E times dA, Our electric field, we remember, is constant, so it can come out front of the integral. So that's E outside of the integral of dA equals E times A, and this is area of the Gaussian surface. So it's the area of that plane I shaded in. Okay, I've got E times A. All right, let's do the flux of the back next. I'll pick a different color. Flux of the back. So now my back is out here, or this part right here. Let's show what dA is. I pick a little bit, and the area vector sticks straight out. Maybe I'll do that in a darker color, it'd be easier to see. Pick the little bit, and the area dA sticks straight out. Over here on the side view, I think that one's easier to see. The area sticks straight out. So the electric field is out, the area is out. Those two guys are parallel, just like it was on the front. So I've got the integral of E dot dA equals the integral of E times dA times cosine 0 equals the integral of E times dA. E is constant, so it comes out front. So I've got E times A. So I've got some flux through the front surface equals the electric field times the area. I've got some flux through the back surface equals electric field times the area. That matches our picture because we see the electric field lines cutting through the front and back. They go outward, so our flux is positive. Okay, last we are left with the sides. So the sides I'll color in green. So here's the side, here's the side, and then it's on the bottom, and then there's on this side. And over here on this picture, these are the sides right here. So let's pick a little area element of our sides. Why don't I pick on the top here? The dA sticks straight up. Okay, and over here on this side, dA would stick straight up. So on the sides of the box that I showed with my little Lego demo, on the sides of the box, the area and the electric field are perpendicular. So flux for the sides is equal to the integral of E dot dA equals the integral of E times dA times cosine 90 equals 0. So our net electric flux is going to be the sum of E times A plus E times A plus 0 to give us 2 times E times A. So E times A plus E times A plus 0 equals 2 times E times A, where A is the area of this surface right here, or this much right here. Okay, the right or the left-hand side of our equation is now done. We've also already done the right-hand side. Let's put them together and find the electric field of the plane. If you'd like to get a head start on what's coming up next and to test how well you understand how to use Gauss's law, how about you try and apply Gauss's law to find the electric field between the plates of a parallel plate capacitor. Assume the plates each have charge Q and area A. One plate, of course, will have positive charge and one plate will have negative charge.